Hello everyone, welcome to problem 3.16 of Griffiths Electrodynamics. So this problem states that we have a cubical box with sides length of A, and they consist of 5 metal plates welded together and grounded. The top is made of a separate material and is held at a constant potential of just V0, just generic constant potential. We want to find the potential inside the box. And then what's at the end, we can also figure out what should be the potential at the center of the box. Alright, so this problem is essentially just solving Laplace's equation in 3 dimensions. So I've written Laplace's equation here, so this is just the partial derivative of v with respect to x twice plus the derivative of v with respect to y twice plus derivative of v with respect to z twice is equal to 0. So that's Laplace's equation. Now, I've stated our boundary conditions here because whenever you're solving a partial differential equation, you also need to know your boundary conditions. So we know that when the potential at z equal to a, so z is this axis, x is coming in and out of the board, y is going this way. At x, y, and a is equal to a is this top surface, that's equal to v0. All the other surfaces, so when x is 0, so this side, the potential is 0. When x is a, so this surface, x is 0. When y is 0, so the back wall there, the potential is 0. When y is a, so this front surface here, the potential is 0. And when z is 0, so the bottom of the cube, potential is 0. So that's just our boundary conditions. And I'm not going to go through all of this because if you have the textbook, Griffiths goes through solving this equation using separation of variables. And so you can do the same thing as Griffiths does, except you get to a point when you separate this equation out, you get 3 ordinary differential equations. And there's a separation constant that comes along with this. And in the example that Griffiths does, he sets this k squared plus L squared term, he applies this to the x equation. But this, if you have your constant like this defined as this for the z equation, whatever equation has a constant defined as this, gets this minus sign here and gets this equation like this, which gives exponential solutions. And intuitively, you can figure out, hey, maybe there should be a, in the x and y direction, there's no real dependency of the potential. Kind of, like the potential as the height changes is going from v0 at the surface all the way down to 0. And so maybe the potential in the z direction has some kind of exponential decay kind of term or whatever. So we kind of make an educated guess to put this constant term, the k squared plus L squared term, defined this way on the z term, and then have the x and y ordinary differential equations just have the k squared and the L squared and the y. If you don't understand how this happens, read the textbook. I don't know if one of my other videos I go over this in a little bit more depth, but there is a great example in the textbook of how you get to this point. And then I chose to put this constant with a different equation that he does in the example he does. So once we have these 3 equations, this isn't a course on solving ordinary differential equations, so these are pretty standard second order constant coefficient differential equations, and they have pretty known solutions. So the x equation has this solution, so it's a sine of kx plus b cosine of kx. The y equation has c sine of ly plus d cosine of ly. A, b, c, d, these are all constants. And the z equation has e to the square root of L squared plus k squared z plus f e to the minus k squared plus L squared z. That's, yeah, I don't know why I have it equal to 0 here. That must have been a remnant of something else. But these are the three solutions you get to these three ordinary differential equations as defined as this. So really this problem is about taking these known solutions, because the solution what we're trying to do is we're saying that we're using separation of variables is essentially saying, hey, our potential function, we're guessing, or we're kind of forcing it to be, a product of three different functions of a single variable. Oops. Yeah, like this, right? So if we know these, we just multiply them all together, and that's going to be our solution. But this technically is correct, but it's not going to fit the boundary conditions yet. So we need to apply our boundary conditions to sort of get a more correct solution for the specific problem. So let's look at this condition where x is 0. So when x is 0, the potential is 0. So if you plug in 0 here for x, well, sine of 0 is 0, so this whole term goes away. Cosine of 0 is 1, so what we get is just b is equal to 0. So in our solution, we're not going to have this second term with b, because b is 0. Now let's look at our other condition where x is equal to a. So ignoring this term now, because this term is no longer a part of our solution because it doesn't fit our boundary conditions, because b is 0, we just have a sine of ka is equal to 0. The only way this holds true is either if a is 0, which then means this whole equation is 0, this whole function is 0, which then means our whole solution is 0, which is like, sure, it's a solution, but it's not interesting. It's not the one we're looking for. So that means that sine of ka must be 0. Well, when could sine of ka be equal to 0? Well, sine is equal to 0 at integer multiples of pi. So that means that the argument of sine ka must be equal to an integer multiple of pi, where n is just some integer 1, 2, 3, whatever. And so that means that our constant k must be n pi divided by a, where a is remember the length of the cube here. So this condition puts a restriction on what our separation constant k has to be. Now let's look at y. So when y is 0, we get a very similar situation. The c term drops out, and we get d is equal to 0, essentially. So for our y function, this term is not in our solution. We just have the sine function. And then similarly as above, when we plug in a to y, we get that L by the same exact argument is equal to m pi over a, where m is a different constant, or a different integer, 1, 2, 3, whatever, that is independent of the one over here, n. So now we have these conditions. So looking at the last boundary condition, when z is equal to, let's see, when z is 0, what do we get? So plugging in 0 for z, this will just give us e to the 0 here, e to the 0 here. Anything to the 0 power is 1, so we just get e plus f is 0. So that just tells us that f is equal to minus e. So just plugging that in there, that's what we have. Now, if you recall, if you've ever learned this, the hyperbolic sine functions are defined by exponentials in this way. So, the hyperbolic trig functions, I should say. But hyperbolic sine is defined as this way, as e to the x minus e to the minus x over 2. And if you look here, x here is just the square root of k squared plus l squared. So this is like e to the x minus e to the minus x. We're just missing the 2. So that means that 2 times the sine of x is just e to the x minus e to the minus x, which is what we have here. So then we can rewrite our z function as 2e, so this is just a constant, times hyperbolic sine of x, where our x is, this should have z, or sorry, no, actually, yeah, there's a z missing up here. I don't know why I didn't write it. But our x is just the square root of k squared plus l squared times z. So this is just a nicer way to rewrite our solution. All right, so now, basically, if we just take and multiply our solutions now, what you would get is a single function that would satisfy the boundary conditions, and it'd be like a function of n and m, right? Like depending on the integer n and m you choose, you get a different solution. If you just, multiply x, y, and z, but x, y, and z have n and m in them, and so it depends on, what integer you choose for each of those. So in fact, there's actually an infinite number of integers, right? So instead of just having, using a single solution, this equation is linear. We can do a superposition of solutions to get a bigger solution. So essentially, we're just going to sum over those integers n and m to have a superposition of solutions. So in doing this, we just have our two summations over n and m from 1 to infinity, and we have a constant, which, I just took all the constants that were in the other equations and combined them together. And when we take a superposition of these solutions, there's going to be a coefficient term for each term in the superposition. So that's what this constant c sub n and m is, because it's going to depend on, like, this constant is going to depend on what value of n and m we're on at the moment. And so the x solution, when we multiply these out, if you remember b0, so we just have our sine of kx, which is, remember, k is this, so we have sine of m pi x over a, and then the y is just sine of m pi y over a, because the d term here is 0, so we just have this for y, and then we have this for our z, and remember, I removed the constants out and combined them, so we just have our hyperbolic sine function, as we saw here, where I plugged in k and l as m pi over a and m pi over a accordingly, and then yeah, the last thing I did in this last step is I rewrote it all, and this square root term can be simplified as just, you can factor out pi over a squared, so we just have pi over a outside the square root, and we just have n squared plus m squared in the square root. So that's just a more simplified version of this solution, and that is the solution to this partial differential equations that fit the boundary conditions here. Now, well, not quite, we still have one more. We don't know what this constant is, the coefficient term for each of our terms in the summations, right? So we can use Fourier's trick, which has been shown, how to do that in the textbook, but essentially what we're going to do is multiply. I wrote the boundary condition here, so remember the last boundary condition is when z is a, we have a constant potential. So we're looking here at this boundary. So plugging in a for z, what you get is, all you get here is z, the only z is here. So plugging in a cancels the a on here. So now there's just a pi, and this actual, like, hyperbolic sine term here is just a constant. Everything here is a constant. N, m is a constant, pi is a constant, so this is just a constant now. And this whole thing is equal to v naught. So if you multiply both sides by two integrals, so we integrate once with respect to x, once with respect to y, and we multiply those integrals by we integrate with these two sine functions where n prime and m prime are different integers than n and m. I just used the prime notation to kind of differentiate them. So what you're seeing here is the right side here. I just moved it to the left side at like beginning of the equation because it's easier to see. So we're multiplying by these two integrals. We're integrating from x equals 0 to a, y equals 0 to a, and sine of m prime pi over ax, sine of m prime pi y, and then we're integrating with x and y here. So this is what we multiply on both sides. So looking at the right side, we have our summations, we have the term we're trying to solve for, and then I pulled out the hyperbolic sine term because it's just a constant. And then I grouped the two integrals here for x's and y's. So we have, this sine term will be integrated with the m prime sine term, And then same for this y sine term, we integrated in the y integral with the m prime sine term. And these integrals are something you should have seen before if you've done the examples in the book. Essentially, these are doing what's called like the outer product of these two functions. And the sine functions are orthogonal to each other. And so these two integrals here will actually be 0 unless n and n prime and m and n prime are the same. And when they're the same, then what you get is just, in this case, it's going to be a over 2. But if like the length of it's the length of whatever the boundary is of your thing is over 2. So if it was 1, it'd be 1/2. But in this case, it's a over 2. Or more generally, L over 2, where L is just the length of your system. So these two integrals cancel out the summations because the only terms that will survive in these summations will be the terms where n and n prime and m and n prime are the same. So we no longer have a summation, we just have a single term, and n and n prime and m and n prime can now be just thought of as the same variable because that's the only terms where we actually get a value. And rewriting this on the other side of the board, I believe, let me look. Hang on. I'm gonna flip it. There we go. So, I think I just rewrote this here. So we have this side of the integral, which still has the integration. This was the side with the terms where, remember, both of those integrals evaluate to a over 2. So then we have a over 2 squared because there's 2 a over 2s, and you just multiply them. So basically all we have on the other side is just the coefficient term, a over 2 squared, and the sine hyperbolic term, which is just a constant term. And then on the other side, we have this integral still to kind of evaluate. So solving though, but we have an equation here for our coefficient. So solving for our coefficient, basically dividing by the hyperbolic and multiplying the other term over, you get 2 over a squared, v naught divided by this hyperbolic sine term, and then the integration of the two sine functions. And this is essentially your equation for the coefficient term. However, you can simplify this because this integral can be evaluated. So doing this integral, I mean, these are just two different integrals. These are simple integrals. One with respect to x, one with respect to y. You're just integrating sine. So the integral sine is minus cosine, right? So, you know, everything out here stays the same. The two integrals evaluate. When you do an integral of a sine function, you also divide by the terms inside the argument assigned. So we get an a over n pi and an a over n pi constant from the integration, and then minus sine times minus sine is just or the integral of sine is minus cosine. So minus cosine and minus cosine, the two minuses cancel out, so there's no minus sign in here. Well, we just get cosine of n pi x over a and cosine of n pi y over a from the integration. However, we have to evaluate these two respectively, where x and y go from 0 to a. So out here, what I've done is, so the a's here, I can pull out, they're just constants. They're not going to affect the integration evaluation. So that's a squared, they cancel out. 2 squared is 4, right? That's where I got the 4. And then the m pi, the nm come out, and then pi squared because pi times pi. And so I just grouped all these constants out here. And then evaluating the x1 from 0 to a, plugging in a here gives us cosine n pi minus cosine of 0, and then the y1, cosine of n pi minus cosine of 0. Where cosine of 0 is just 1, so everything out here stays the same. We just have cosine of n pi minus 1 times cosine of n pi minus 1. And if you evaluate these terms, like cosine of n pi or cosine n pi, those are the same terms. It's just different integers. But that will be 0 when n is even. So when n is even, you have integer multiples of like 2 pi, 4 pi, 6 pi, 8 pi, which is just the same point on the unit circle. And cosine of that is just 1. So you get 1 minus 1 here for every even integer of pi. So when n is even, it's 0. When n is odd, you get a -2 because you're on the other side of the unit circle, and cosine of -1 is negative. Cosine of negative pi is -1. So -1 minus 1 is -2. So when n is odd, you get -2 times -2, which is 4. So then that 4 times this 4 is 16. And what we eventually get is just this big constant here. So this coefficient, c sub nm, and why I wrote it like that is because the coefficient depends on n and m, a lot. So that's why, it'll be here in our solution within the summation, because depending on what the summation term we're on, n and m, will determine what that coefficient is. So that's our coefficient, plugging everything back into our equation from before. We're just replacing the c and m with the actual term we calculated. So there are summations, the term we just calculated, and then sine of n pi x over a, sine of n pi y over a, and the hyperbolic sine function, where there should be a z in here. So we have the hyperbolic sine of pi a squared root of n squared plus m squared z. And so this is now our solution to the full differential equation fitting the boundary conditions. So that was a lot. There is one more part to this question. It simply asked us, like, what is the potential at the center of the cube? And I thought about this a lot, and I found a solution that's a bit of a more conceptual way to solve it. So, our cube here is just a cube with one side, right, where one side has a constant potential V naught. So imagine if you could make a superposition of cubes, of 6 cubes, right? I'm gonna maybe try to draw it here. Let's see. So imagine this face had a potential V naught, right? You could orient the cube. You had 6 of those cubes, and you could orient them however you want. This face had V naught. Anyways, you basically orient these cubes to where you have 6 of them, and you orient to where the space between the cubes is basically a cube where V naught, there's a potential V naught on every surface, on each of the 6 faces within the space between the cubes. I'm not sure if I can really draw this effectively. No, I did not draw that right. So you would have one on this side, one on this side, right? What I'm trying to get at though, is in that case where you have a cube where every face has a potential of V naught, well, the potential at the center has to be V naught, because going from the top to the bottom they still have to be V naught. So the potential within the entire thing has to be V naught. However, in our case, where we just have a single side of V naught, then we could argue that the potential at our center, where just one side is V naught, is just a 1/6 of that. So if the potential at a center of a cube where all the faces are V naught, then the potential at the center of a cube where just one of the faces is V naught is just a 1/6 of that potential. So anyways, that's the conceptual argument to be made. And so, the potential, the V at A over 2, A over 2, A over 2, or whatever, the center of the cube, I argue is V naught over 6, or is 6 of the potential, whatever this is. And you can numerically check this by using something like Mathematica. I actually urge you guys to do that. Choose some value for V naught, evaluate this whole thing, and see if this lines up. So, anyways, that's my argument for the potential at the center. I don't have much more than that. So, if you guys enjoyed this video, please leave a like. Leave comments if you have questions, and make sure to subscribe for more. So I'll see you guys on the next video.